All right, so it looks like it's time. We'll go ahead and kick things off because there's a lot of content to cover and try and fit into 45 minutes. Actually, I didn't realize that this session was going to be videotaped, and it really does kind of increase the pressure. Like they say, the camera, like adds at least 5 kilos, and that's definitely true. So I want people that are watching on YouTube or whatever to know that, like face to face, I'm actually like totally ripped. Didn't expect people to laugh at that, but yeah, okay. All right, so let's jump into it. Yeah, this is me. So basically, my day job is fixing hotspot bugs, and yeah, I do some evangelist stuff. I was the update project maintainer, or one of them. I tweet, I blog. I'm over here on the left. Yeah. So today we're covering bytecode. I think everyone knows what bytecode is, but we're going to start from the very beginning just to make sure everyone's on the same page. So we're going to start with an introduction, lay down some foundational concepts, and then basically the gross majority, the payload of this talk is really the examples as we step through each example one by one and kind of see how the Java code maps to the bytecode to get an idea of how it all works. So why would you want to study this in the first place? Well, basically, bytecode is really the only common language that we have for the JVM ecosystem. So we have all this other stuff running on top of the JVM in addition to the Java language itself. Obviously, there's other languages. There's bytecode that's generated or spun during runtime using Azam and different libraries like that. So there's all these different sources of bytecode. And the only thing in common is that they all eventually end up as bytecode when they're run by the JVM. So to understand what's running, really it's the input that the JVM takes in. And so you're limited if you don't kind of speak that language, so to speak. There's lots of cases when you're kind of debugging some really hairy situations where being able to look at individual classes and examine them using the Java P utility is very, very useful. Obviously, there's tools like decompilers and stuff like that that try and reconstruct the Java code that corresponds to whatever bytecode or class you might have. But it's not always possible to reconstruct Java code from bytecode because bytecode is more expressive than Java code is. You can do things in Java bytecode that you're not allowed to do in the language. For example, you can take a monitor in one method and then release that monitor in a different method, and you're not allowed to do that in the Java language itself. The specification doesn't let you write code that way. But as far as bytecode is concerned, that's perfectly legal. So unless you can kind of use Java P and look at the raw bytecode, there's cases where you'll be looking at stuff like classes that there's no way you can decompile it into familiar Java code. Also, it's a really important foundation for further studies. So there's things like type erasure and bridge methods and certain debugging techniques that just are not available to you if you don't have a good working of bytecode. Another thing I would point out is that it's kind of low-hanging fruit in terms of what you can study. Lots of people think of bytecode and that it must be as complicated as assembly code. Just to give you an idea of who I'm speaking to here, how many people here have assembly coding experience? Wow, okay, so most people, all right. Java bytecode is actually easier than assembly. I mean, I've got about 3 decades of Intel assembly under me, and I still have to be looking at references as I code. And there's still things that I come across every day that I'm like, what? And it's still changing and it's growing. And anybody that tells me that they really understand the AVX instruction set, I think they're lying. Whereas in bytecode, you can really, you can get in about an hour. You can just take one class and really get all the foundational concepts under your belt. So it's not that hard to learn, and there's a whole lot of benefit to doing so. So we're going to do that today. For using Java P, how many people here have used Java P to look at a class? Okay, a good chunk of people. So Java P, if you haven't used it before, just a few really quick tips. So this is just something that basically is like a disassembler for a class file, and it's going to give you output that will show you what the bytecode looks like, basically the assembler version of bytecode. And when you use it, the V option, the verbose one, is going to give you the disassembly, and then -P will give you the private methods. So generally, when you're looking at a class, an unknown class, you'll use a -V, -P. And also, this is something a lot of people kind of miss, is that Java P is improved dramatically, and it's always backwards compatible because the platform itself is backwards compatible. So when you're using Java P, I always make it a point to use the absolute latest Java P from whatever JDK I can get my hands on. So even if I might be examining a class that was compiled for JDK 7 as its target or whatever, I'll go ahead and use Java P from Java 12 or whatever, just because there's bug fixes that have gone in Java P. There's lots of improvements in the way the output is presented to the user that makes it easier to understand. So always use the latest Java P that you can. Now, I said the payload to this talk, most of the really good content is a bunch of examples. And these examples pretty much all come from the Java virtual machine specification. So if you've read this document closely before, a lot of this is going to look really, really familiar. That said, a dry just reading of this document from beginning to end, while helpful, is not really as easy to understand as we might want it to be. And so part of the goal of today's talk is to kind of graphically show what each of these different instructions, how they operate on the stack, how they behave in a more intuitive form. So what is bytecode? Why is it called bytecode? Well, should be kind of obvious, but it's code that comes in bytes, right? Each of our opcodes is only 1 byte long, and so that gives us specifically 256 possible bytecodes, which is a really, really small space. So that's one of the reasons why we're very conservative about adding new bytecodes to the specification. Like when Invokedynamic was added, that was such a big deal because a new bytecode had not been added in, I don't know, maybe something over a decade of Java's history. So there's a very, very small amount of space that we have to add new bytecodes, and so we do so only after kind of all other options are exhausted. Now, the operands are 1 byte long, or I'm sorry, the opcodes are 1 byte long, but the operands that we pass to them, the arguments, can be 1 byte or 2 bytes long. And so the entire instruction is usually somewhere between 1 and 3 bytes long. Now, the machine itself, the architecture, is a stack machine. So for example, how easy is this to read? Can you see the push 1 over here in the red? Hopefully people can read this. The coloring here is kind of unfortunate. So if I want to add 2 numbers together, I can say I can push the value 1 onto a stack, and then I push the value 2 onto the stack on top of that, and then I use an add command to add those 2 numbers together, and the result is left on the stack. So most instructions kind of follow this pattern where they take their input from the stack and then they put their result back on the stack. And this is really nice for us because basically it allows us to generate code in a way that's completely CPU independent. And so normally when you think of low-level machine-level type code, you think of working with individual registers, but that's obviously very closely tied to the hardware that you're running on. Certain, especially like very orthogonal or non-orthogonal CPU architectures like Intel, only certain registers can hold certain types of data, or certain instructions only work with certain registers in certain ways. And all that just goes away when you're working with a stack architecture because there are no specific registers. Everything's just on the stack. This kind of design is really common. Anyone that's used like an HP, a classic HP calculator, is going to be familiar with kind of the stack notation. And of course, PostScript is a stack-based virtual machine as well. And it's interesting that James Gosling, before he worked on the Java project, worked on the news project at Sun, which was basically trying to use PostScript type language to display stuff on the screen and kind of be like an X Windows or an X Windows server, X11 server type situation, but using PostScript as the language. And so he had a lot of exposure before he went to design the Java platform with stack machines and how they work. And of course, Forth, which is also extensively used in Sun hardware as in our Open Boot and stuff. So we have this concept of local variables, which are basically memory locations, and they're independent of the stack, and they usually correspond to what we would consider local variables in the Java language. And so there's a number of commands that allow us to basically move data between the stack and local variables. And they're also, these same commands are used to handle method arguments. And so when we pass a value to a method, the way we access that value that's been passed to us as the callee is to use the same commands that we would use to access local variables. If that doesn't sound very intuitive, when we actually see some examples, it will become easier to understand. So let's go look at some examples. So we're going to start off with some very, very, very simple Java code. So we call this one spin because basically it's a for loop and it spins 100 times. So we have our index, which is a 32-bit integer. It's Java, so it's signed obviously, and we're just going to count from 0 to 100, and it's a busy loop. So what does this look like when Java-C gets a hold of it and turns it into bytecode? Well, the Java P output corresponding to that bytecode is going to look something like this over here on the right. And you'll start off before we even have the individual instructions. The instructions all here, they have bytecode indexes on the left of them. But before we have the instructions, we actually have three very critical pieces of information: the stack, locals, and arg size, that give the JVM information about like what the constraints should be, what this method is going to require in terms of resources to execute. So stack 2 just says, hey, I'm going to have a 2-element high stack. So my stack can grow up, go between 0 and 2, but it'll never go beyond that. So 0, 1, or 2 high. And so that if for example, the JVM is allocating memory to handle all the stack operations, it knows how much memory it would need to allocate at this point. And then we have the number of local variables. And so we're saying that there's 2 locals here, which right off the bat, this might seem kind of strange, because if I'm looking at my Java code, I see that I have this integer here, but there doesn't seem to be any other local variables. And we'll get to that in a second. And then we have this argument size thing, and this is saying this is 1 argument. So you'll notice a few slides earlier, I said that we treat arguments like local variables, and we can see this here. So this locals here, this total number, is actually what we would define in the Java language as a local variable, and the other one is an argument. So 1 argument and 1 kind of Java level local variable. So it's obvious here what the Java level local variable is. Can anyone think of what the argument is here? Yes. So this is a virtual method. It's not a static method. So even if we don't use it, there is a this pointer that is being pointed here. So we start off here and we have our this pointer, and then we have another local variable that at the beginning is initialized. And as long as this code is passed bytecode verification when the class was loaded, we can be assured that the code's not going to try and access this other local variable location before it's initialized with some value. So let's jump into the actual instructions. So we start off right here pushing a constant 0 onto the stack. So there's several instructions that basically just take very, very low value constants and push them onto the stack. And so you only have like 0, 1, and maybe 2, I think. And it depends on the data type to which constants are available. Otherwise, you'd have to be loading these values from the constant pool, which we'll talk about a bit later. But for here, so I'm just saying I have this I const 0. So it's saying I'm taking a constant 0, and it's an integer. I'm treating it like a 32-bit int here. And I'm putting it there. And then I immediately have this I store 1. And again, you'll see this pattern again and again and again with Java bytecode, but the first letter generally indicates what the data type of the value that we're manipulating is. So here, this is an integer so it's taking the integer that we just stored here, and it's storing it in local variable slot number 1, and these slots are 0 indexed. So local slot number 1 would be the one that's basically right above the this pointer. Anytime you have a non-static method, the this pointer is always in local slot 0. And so local slot 1 is the first one that we have available for our use as local storage. So it doesn't really make a whole lot of sense right now, but for whatever reason, we take this 0, we stick it onto the stack, and then we immediately move that over into a local variable slot. This will make a whole lot more sense in about a minute. So then we go and we load this value back from the local variable slot to there. So we put the constant there, we've copied that constant, or we moved that constant over to the local variable slot, and then we moved it back. So the effect of these 3 commands is basically we've written 0 here. So we've initialized this local variable slot to 0, and now we have a 0 on the stack. Now we have this byte integer push 100. So this is a command that takes a byte-sized operand, and it says, basically whatever this operand is, put that onto the stack. So we're taking 100 and we're putting it here. And now if you're thinking in terms of what is up here in the Java code, you might start getting a feel for what we're going to be doing here. So now we have a branch, and we're saying that if this integer compare greater than jump to 14. So this is a bytecode offset. Each individual bytecode has an offset that is printed here on the left of it. And we can see that 14 is basically the end of this method. So it's us leaving this block of code here. So we have these two numbers here. These two numbers that are on the stack become the input of this branch instruction of this branch instruction right here. So we suck them in, we compare 0 to 100, and if the number at the top of the stack is greater than 100, then we're going to jump here. But otherwise, we're just going to continue. We're going to fall right through this branch. And so we have this integer increment thing that allows us to specify an arbitrary slot location and increment it by some byte amount here, and in this case 1. So we're saying that slot number 1, we want to increment that by 1, and that's what just happened here. And now we just go back to 2. So that may seem kind of obtuse. It's kind of hard to really follow that the first time around. But then when you look at this, okay, so this is our loop right here. So basically, every time we do this, we start off, we load the value from the local variable slot, which is right here. We compare it to 100, which is what these two instructions do. And then if we're not at 100 yet, we increment it and we loop around, which is exactly what we're doing in the for loop. So we basically just keep going through here until we go through this loop 100 times. And then when we finally get to this branch instruction here, and this is 100, we compare it to 100, and we'll jump out of the loop. And that's about as painful as it gets. It's really like once you wrap your head around one example, then everything else kind of falls into place. So let's take exactly what we just did with an integer, but instead of using an integer data type, let's replace that with a double and see how the bytecode changes. So the only difference between the code we were just looking at is in these 3 places. So obviously the declaration for this local variable is no longer an int, it's a double. And then our constants here are 0.0 as opposed to 0 and 100.0. These are floating point values. And all of a sudden, the bytecode that's generated looks significantly different. For one thing, it's longer, right? And so we're like, whoa, that's pretty strange. I mean, we realized that earlier, we had all these instructions that started with I, because we were dealing with integers. And so when we just replace all those instructions with D, like why would the bytecode get longer? So let's go take a look at what we've got. So at the very beginning I said, we've got these 3 pieces of information that basically say this method is going to obey these constraints about stack size and locals and arguments. And if we look here, the stack is 4. Now, the integer spin, it was example, the stack was only 2. So right off the bat, this is kind of weird. Like we have twice as many pieces of data, that's weird. And locals is no longer 2, it's 3. And arg size is 1. So arg is again going to be this pointer, right? That's not changing. But it seems like everything else has changed. And the reason it's changed is because different data types actually fall into one of 2 categories based off of how much kind of space they need to take up. So pretty much the only thing you need to remember is that long and double are, for lack of a better way to explain this, they're basically 64-bit values for all intents and purposes. So they take 2 kind of chunks. They're 2 integers worth of space to store and manipulate them. So long takes 2 chunks, 2 slots, so to speak. Double takes 2 slots, and every other type only takes 1 slot. So if you just remember that long and double are unique, long and double take 2, and everything else takes 1, then you can remember how this works. The one thing that might be kind of surprising or interesting here is we'll notice reference here only takes 1, and that's completely platform independent. So even if your JVM is 64-bit, which most JVMs we use are 64-bit today, a reference, whether it be a reference into the heap or whatnot, is going to still only take up 1 slot. And that's because the JVM is an abstraction from the actual hardware you're running on. So the fact that the actual hardware you're running on is 64-bit really has no direct impact into how we represent an algorithm in bytecode. Those are 2 different things. So everything, you can think of it kind of as, I'm cheating here, but you can think of it as being a 32-bit value. except for long and double. So let's go back to our spin examples. And so this is the first one we were looking at. This is the integer spin. And you'll see that we would have two int values on the stack, and we were going to compare them. Well, when we switch things to double values, each value now takes up 2 slots. So this one local variable that was a single double value now all of a sudden is taking up 2 slots. And when we have at most 2 separate double values on the stack, now that's taking up 4 slots. So that kind of explains this discrepancy, so to speak, of the stack size that's needed and the number of locals here. So again, we notice the first letter of most of the instructions gives us a clue as to what data type they're working with. So all of a sudden, these are all Ds, and that should not surprise us. Integers started with I, doubles are going to start with D. So this is a new one. This is the load constant to W, which probably is not going to make much sense to you if you've never seen bytecode before. And this is doing the same thing that in the integer example, we had the BI load where we were taking a byte argument or a byte operand, which happened to be 100, and load that on the stack. And we can't do that with floats. We just don't have any way to represent a float constant value in the byte stream. And so we have to load the value, this 100 right here. We store that in what we call the constant pool. The constant pool is just a chunk of the class file format that has our constants in it, our constant values in it. So some very simple constants like numbers that are under 256, for example, byte-sized integers and stuff like that, we can actually just put them as operands into the byte stream. But anything as complicated as a floating point number, we need to actually store that in the constant pool. And obviously strings are another example of things that end up in the constant pool. So because this is a double value that we're loading here, this 100 that we compare our index to every iteration, we need to load that from the constant pool. So constant pool, actually, there's 3 separate instructions that we have for loading values from the constant pool. For category 1, and again, category, we're referring to the size of these operands. So category 1 data types, which is basically everything but a double or a long, can be loaded by either LDC or LDC wide. So load constant, wide do the same thing, except the difference is that load constant takes a single byte operand, and load constant wide takes a double byte operand. So the difference is a constant pool is you can think of it as a table of entries, right? And so each constant value has an index, and these are indexes. The operands to these instructions are indexes into the constant pool. So I'm saying take constant pool entry 3 and put it on the stack, for example. So if you have a very small constant pool, then indexing into that data structure can be done with just 1 byte. But if you have a really big constant pool with over 256 entries, then you need the ability to use 2 bytes to reference somewhere in the constant pool. So basically, any constant pool reference, by definition, that is not of one of these larger types, can be done with the LDCW. But to kind of save space, we have this shortcut version where we can just say, well, if it's a really small constant pool index, I can just use the LDC version. Now, LDC2 is for loading doubles and floats. So same exact operation as what LDC does, except with LDC2, we're just taking something that's twice as big from the constant pool and moving it over to the stack. And this one only has the W version, so the operand is always 2 bytes. It's always a 16-bit index into the constant pool. So here, because what we're loading is a double value, we have to kind of use the W version of this. And so I'm saying take constant pool entry number 2. Now number 2 is a really low number, but we still have to use the wide version of this because the LDC2 doesn't have this shortcut one that takes a byte operand. It only has the 16-bit index version. So slightly wasteful, but the reasoning here is that you just don't work with doubles and longs as frequently as you deal with ints and other smaller data types. So we do that, we do our compare, and you'll notice here also we have, with the 32-bit version, we had one instruction that was the branch. So we did our compare, we took the two values off the stack, we compared them, and then we branched, or we didn't branch, all in one instruction. Whereas with this double value, we have one instruction to basically do the compare, and then another one to say, kind of look at flag values or whatever and say, okay, if that was a greater than situation. So this first one actually leaves something on the stack to say, what the result of that comparison was. And then the second instruction branches based off of that previous instruction's results. So the point here is that depending on the data type you're working with, the instructions that you can use could be limited. And so integer and long both have really amazing support. So over here, I know that the font's really small and you can't really see very well of what's written, but basically at the top we have different data types. So we have byte, short, int, long, float, double, char, reference, yada, yada. And then on the left we have all sorts of different operations that you can do on them, whether it's a load or a store or a mathematical operation or whatnot. And you can see like a type like integer that we have here basically supports, it has its own customized version that supports all these different instructions. Whereas then if you're a short or a byte, you only have the small handful of operations that can work on you. So depending on the data type, the support that's built into the instruction set is very unequal. And so why does this work? So how do we work with shorts and how do we work with byte things and booleans and stuff if we have this kind of crippled instruction set? And the reason we can get away with this is because at the bytecode level, we basically treat most of these data types, anything smaller than an int, as an int. So we say, a byte or boolean, only needs to take up 1 byte of space, or maybe even technically 1 bit, if you want to get really detailed about it. But in practice, we're just going to say that's an int, and we're going to treat it like an int most of the time. And it's only when we need to worry about things like overflow behavior and casting where we need to actually kind of remember what the original type of that particular piece of data was at the Java code level. So this is just kind of a way of getting away and having our cake and eating it too, where we say, oh, we're just going to pretend like all this stuff is an int. And for most cases, the code works that way, and we don't have to think too deeply about it. So again, we see with the int spin example here, we had one instruction here that did the compare, right? It took these two values, compared them, and then branched based off of the result of that compare. And with a double spin, we had to break that into 2 separate instructions. And you'll see that pattern again and again and again. So here, again, it's same pattern again and again and again, but we're just changing the data type. So instead of an int or a double, we've got a short. Okay, and we'll see here that it's almost exactly the same as the original int example was. These sizes, the stack size, the maximum stack size, the number of locals, this all looks like what we were just looking at with the earlier int example. When there's all the instructions we use are the same instructions that are, kind of customized, so to speak, for working with integer values. So what's different? What's different is we have this I2S instruction here. And this I2S instruction is kind of the way of the compiler saying, hey, we've been treating this like an int, but in reality it was a short. So right around here, if you happen to have overflowed, you better truncate that value, so to speak. And so we're going to cut off any overflow if this was really, we went beyond the bounds of what a short value would have been. So just by putting in these little places, where they matter, so to speak, we can make sure that the bytecode is consistent with the Java code, and it behaves like a short, even though most of the time the JVM's not really even concerned or knowledgeable that we're dealing with a short. So let's look at some weird constant pool examples. So here I'm just being annoying and I'm loading all sorts of weird stuff in here to give me an example to show you. I'm loading an integer. I'm loading another integer that's much bigger. I'm loading two long values here, and then a double. So the first integer, again, for numbers that are shorter than 256, I can put that value right into the byte stream. I have this bi push, byte integer push command that allows me to just take the next operand and whatever that value is, put it on the stack. So that's pretty simple. And because I'm storing it in a local variable here, I'm storing it in I, then I'm going to put that in 1. Because remember, a slot 0, because this is not a static method, is always going to be this pointer. So that's fairly easy to understand. For 2, I've got, or I can't even count the number of zeros there, but I think that's 1,000,000 there. So I'm taking some really, really big number here, and obviously I can't fit that in a byte. So I have to load it from the constant pool. So here I have a constant pool load. It's saying constant pool index number 2. If you look at the Java P output, it'll actually help you out, and instead of making you go look up at the constant pool yourself, it'll actually look it up for you and say, hey, that value actually happens to be this. So it just makes the bytecode output a little more readable here. And we're sticking that in local variable slot number 2. For long values, here, because the value itself is just a 1, there's actually a special instruction that's made just for taking a long 1 value and putting it onto the stack. And then we take whatever's on the stack there and put that in local variable slot 3. And then finally, we have this one where it's a whole bunch of f's together, which it's going to be interpreted as 2's complement. And we're saying, so that's going to be a -1 long. And we're loading that from the constant pool as well. And then here we're doing a double, which has the same semantics or the same behavior as what we were looking at when we had the double spin. Again, we have to take this value, this 2.2, and load it from the constant pool, and then we stick that into a local variable. Okay, so how does argument passing work? So we already discussed that arguments are treated like local variables. So if I have this add2 method that just takes 2 integers, 2 32-bit integers, and I add them together and return them, the bytecode's going to look really, really simple. First off, you'll see that the locals here, it says that there's 3 here. So again, it's a virtual method, so there's this pointer, and then 1, 2. So there's 3 locals, so to speak, and the 3 of those are arguments. So there's nothing of what we would traditionally consider at the Java language level to be a local variable here. Everything is actually an argument. So we take 1, right? We have these set up. This is what we've been passed, so to speak. So these are somewhere in memory. It doesn't matter where. It's up to the JVM to actually implement this somehow. But as far as what we're specifying at the bytecode level, we have these 2 memory locations that have been passed in, and they've been populated already with the correct values by the JVM. And so we take I and put it on there. We take J and put it on there, and then we add them together. So we have this value. And then when we do a return, like this I return, a lot of these instructions, they just take whatever value's at the top of the stack, and then that's the return value for this particular method call. So I return takes whatever's on the stack and makes it the return value. And then there's D return and for all the different, and so forth for all the different data types. So what about a static invocation? We haven't seen a static invocation yet in our examples, but you can pretty much know what to expect, right? We're just not going to have this pointer. So exact same thing, except now the locals and argument size are 2 because the only thing we're dealing with are these numbers here. You also notice there's a flag here that says, hey, this is a static method. So it's very clear that this method is defined as a static method, and the JVM knows how to give it the correct semantics. So what if we have a call in here? What does a call look like? So far we've looked at methods that are being called, but what does it look like when we are the caller and we're calling some other callee? So I have add 12 and 13, and what we do is I call my add2 method with the values 12 and 13. Not really exciting Java code, but it's hopefully helpful for us to understand what the bytecode's going to look like. So when we're calling a virtual method, we have to pass this pointer, right? When we are a virtual method, we always get the this pointer passed. So this is basically this load 0 is we're taking what was in slot 0 and pushing it on the stack because it's part of the calling convention. so to speak, for bytecode. When I call a virtual method, the first thing on the stack is the this pointer. And then I'm just pushing these constant values right here. So these are really small values, so they're in the byte stream. They're not in the constant pool. So I just push 12, I push 13, and then I have an invoke virtual instruction that's basically pointing to the constant pool, and the constant pool can contain method references. So it's actually the name and the signature of the method, and it's up to the JVM and the runtime to dynamically link that up and find which method we're actually trying to call, which may or may not be in the same class or might not even be loaded yet, but that's up for the JVM to resolve. So if we do a static call, that's going to be even simpler because we just don't have the this pointer, but we're just basically putting the arguments onto the stack and then calling an invoke instruction, right? Previously we had invoke virtual, now we're doing an invoke static. Same exact thing though, very, very simple. Here's where it gets a little more interesting. Let's say we have a private method here. So it's a little hard to see here, but we have this private int get it, which we return something. And then here I'm calling this from get it near, I'm calling get it. So what is that going to look like in bytecode? And we actually have this other invocation instruction called invoke special. Invoke special is a little weird for method invocation. It's kind of like the junk drawer of invocation. Everything that doesn't fit the pattern that the invocation instructions use ends up in special. And we'll talk about that a little bit more in just a slide or two. We also have Superclass invocation, which also is a case of using invoke special. And so when we have calls, there's actually 5 main method invocation instructions or operations, opcodes in bytecode. And Invokedynamic is interesting. It's very complicated though. It's added in JDK 7, and I have a whole session just on Invokedynamic that I'm doing this week. So if you actually enjoy this and you stayed awake through the whole thing, you might be interested in checking out the Invokedynamic talk I'm doing some point later this week. We're not going to worry about that right now because it's relatively new and the basics are kind of better to take on first. So the basics are these 4 up here: invoke virtual, invoke static, invoke interface, and invoke special. And just from their names, it should be fairly obvious what most of them do except for invoke special, which is the weird one, right? So invoke virtual, that's the default calling. So the rule here is when we invoke virtual, we have a this pointer, and we do dynamic, lookup, virtual lookup based off of the this pointer. So it doesn't matter what the calling code, it doesn't know what type it's actually holding. It could be A or it could be a subclass of A. And we have to actually look at what that pointer is pointing to on the heap, what this pointer is showing us to know what method to actually call, where to find the implementation. So we invoke virtual gives us virtual lookup that we need the this pointer for. Invoke static, there's static linking, so there is no virtual lookup. We know statically at compile time what method we're calling. That's how static invocation works, right? And nothing new. This is just the Java language. Invoke interface is basically just like invoke virtual, except we're calling an interface method as opposed to a regular virtual method, but it's more or less the same implementation. It's just more complicated underneath the covers. But again, just like invoke virtual, there's a this pointer, and we do a virtual lookup. And then everything else, all this kind of junk drawer of invocation semantics goes into invoke special. So we have constructors, we have superclass, and we have private. And those at first don't seem to have anything to do with each other. Like why do all those use the same invocation instruction? And the reason is unlike the 3 others, these have static linking and they have a this pointer. For these other 3, they follow this basic pattern where if you have a this pointer, you do virtual lookup. If you don't have a this pointer, you don't do virtual lookup. That's the general rule that the other 3 follow. But invoke special is weird because despite the fact you have a this pointer, you don't do a virtual lookup. It's statically linked. So let's look at a concrete example and think about that a little bit. Like for constructors, when you call in a constructor, there's no way for you to override what, like when you call new, you're creating the instance right there on the heap, right? Constructors do not get overridden. So we don't have virtual lookup of them. When you call new, we know exactly statically what implementation is going to be called. But of course, we have to initialize the value. So there is a this pointer there. We're actually taking the stuff. So we see that we have that strange pattern. Superclass calls are the same way. When we make a superclass call, we statically know I'm calling, you actually say in your Java code, the class name or whatever, I'm calling this class's implementation. So that method that you're calling might want to look at the this pointer and have access to the fields of the object that you're handing it, but it doesn't have virtual lookup. It does, we know statically when it's at compile time, when you run Java C, what implementation is being called. And private invocation is, of course, the same way as well. Because if you think about it, when you call a private method, there's no way to override a private method, right? It's private, it's internal to the class itself. So again, when you call private methods, there's a this pointer involved, because we might want to be able to look at fields and stuff, but there's no overriding, there's no virtual lookup that's done. So let's talk about how new objects are created. So this is actually pretty straightforward. It's a pattern that you'll see a lot in bytecode, so you should be able to recognize it, is that we have a new instruction. So we have an instruction that called new, and that does what you think it would do. It just allocates memory out on the heap. What it doesn't do is it doesn't initialize anything. It doesn't call the constructor for you. That's more of a high-level thing that Java does for you. So new will allocate memory, but it doesn't call the constructor. So what we need to do is, you can see down here, we're calling invoke special to call the constructor, and constructors have this kind of int in angle brackets to let you know that they're a constructor at the bytecode level. But when we're calling the constructor down here, but what we need to do first is, by calling new, we say, hey, I want you to allocate this much memory for me. We know the object size. And so we have a pointer on the stack that's a pointer, it's a reference into the Java heap that's saying this is the memory that was allocated for you. So regardless of how big the object that you just allocated on the heap was, this is the static size here. This is just a reference into the heap. And then we have the dupe command, which just basically copies whatever is at the top of the stack and gives you another copy of it. So we have two references pointing to the same location on the heap. Okay. And then when we call invoke special, so invoke special, a constructor just basically takes a this pointer and any other arguments that might be required if that constructor has arguments. And so here, we're taking one of these baby pointers, gets kind of fed to the constructor right here, so to speak. So that gets taken off the stack, but the result of that, the side effect of that, is that now this baby's pointing to an object that on the heap has been initialized. After this constructor returns, now we have all the wonderful guarantees that the Java language gives us that say that, hey, this is not just random uninitialized memory. We've actually done this correctly and followed the language spec here. So you'll see this new to allocate memory duplicate, because we need to call the constructor, and if we didn't if we didn't copy the pointer, then we'd only have one pointer. The constructor would eat it off the stack, and then we initialized something, but we don't know where it is. So to kind of have a method, or to have a pointer left over to know what we initialized, we have to copy it here with this dupe instruction. We call the constructor, and then here, because we're actually returning, our return value is a reference here, we use the a return. So instructions that begin with A, you can think of A as meaning address. So it's basically a pointer. So just like I, whatever was for integers, and D, whatever was for doubles, A, whatever means for references or addresses. So field access is very, very simple. You basically have the put fields and get field instructions that will take the name of the field as a string that it's referencing in the constant pool. And so in one case, you're putting the object down there. So here, like say, I'm gonna set the value here. So my argument is 1. So the argument is in local variable slot 1, and then this pointer's in 0. So I just basically put those on the stack, and then when I call put field is smart enough to say, oh, you want to put this in this field called I that was referenced from the constant pool. And getting values is kind of the exact same thing here, except it's simpler because we only have to pass one argument to it. I'm almost done. So, and we have opcodes that deal with arrays. I'm not going to go through these each one by one, but basically we have ways to allocate arrays. We have ways to allocate multi-dimensional arrays, and then we have ways to store and load arrays, or store individual values or elements from an array. We have switch statements, which interestingly can be translated into two different patterns in bytecode. You can have one where you have everything's in order, so it's like 0, 1, 2, and so it's very easy because everything is consecutive to lay out a table that's efficient, and that'll give you a table switch. But then we also have what's a sparse one. So if we have like -100 and 0 and then 100 and stuff, and so we have all these kind of values that are not contiguous, then we'll have a sparse jump table. But that's really just an implementation detail. We also have a whole bunch of operands that do duplications and swaps and stuff, and this is very familiar if you've ever programmed in Forth, just for stack manipulation stuff that are untyped. So they don't care if they're dealing with integers or doubles or floats or anything like that. They just treat values on the stack as these raw data items. Exception handling is handled by exception tables, where we sit there and say that, hey, if you have an exception that's thrown in this area, from here to here, here's the try block. These are the bytecode indexes for the try block. Jump to 7. So here's this code here is your exception handler code that you can see. And then finally, there used to be a jump to subroutine and return instructions that were provided to implement finally clauses, but the escape analysis and stuff for those is just really horrible for the JVM to do. So we actually dumped those in JDK7, and so they're not used anymore in the bytecode thing. So you really shouldn't see jump to subroutine and return in bytecode anymore. And that's it. I mean, basically, I know I've rushed through everything at a crazy pace, but that's bytecode. I mean, there's Invokedynamic talk, but you pretty much know Java bytecode at this point if you followed along with this 50-minute explanation.